Nasrat Haidari,
Karmjot Singh,
Dianna Man.
and we are here from San Jose State University to present our joint project for ME 154 and 106 with Dr. Lee and Dr. Furman. For the purpose of this video, we will focus on the designing and the functionality of the forward mechanism. So in order to design the mechanism, we were required to have a forward mechanism that can go to three positions: the starting of the apple, to the middle, and to the end. We used a graphic analysis that we learned in ME 154 class, and we came up with this design. The design had a little bit of obstacles. We couldn't use different shapes and apples with this design we had. So we used a retractable spring control peeler that can go through different positions and different sides of the apple.
The following drawings are used as reference to all velocity and acceleration analysis. This is our full linkage assembly drawing. This is our 4-bar linkage assembly drawing where A is the input link, B is the coupler link, C is the output link, and D is the ground link. Arguments include having an input angle of 60 degrees, angular velocity and acceleration of 0.0116, and we assume that our mechanism is running at room temperature, it has no friction losses at the joints, and there are no excessive gaps between the joints and links. Grashof condition is met, however, due to our design parameters, our linkage is unable to make a full revolution. We use the vector loop equation from the DOM textbook to determine the angles theta 3 and 4. Using Excel, we found the angles theta 3 and 4 and their angular velocities, using the lengths of the links and angle theta 2. We use the same vector loop equation to find the angular accelerations alpha 3 and 4. Then we use Euler's identity to find linear acceleration. Using Excel again, we found the angular acceleration for links 3 and 4 using an input angle of 55 degrees. Then we calculated for their linear acceleration.
So for the force analysis, we start off by creating a free body diagram of the whole system. Using the free body diagram, we find the equation of motions for each link for the 4-bar linkage. For the force analysis, we assume that there is no torque relative to ground. Also, there is no applied forces to the peeling mechanism. Using the equation of motions, we create a matrix from which we calculate all the forces in between the links. Here are our results for the force analysis. From the force analysis, we concluded that the servo motor that we picked is sufficient for the torque that we need.
Now that the force analysis is done, we can now look at the stress analysis. Here are some assumptions and material characteristics. Using the formula shown, we were able to calculate the tear-out stress, bearing stress, and the buckling due to axial loading. These are the stresses we found for the tear-out at the driver diet link, bearing stress at the nylon joint, and the stress of each supporting rod. Here are the safety factors found due to tear-out stress, bearing stress, and buckling.